Okay, welcome everyone to the February 1st, 2022 Open Planetary Lunch Talk. My name is Chase. Our speaker today is Marc Costa with NAIF, and he'll be talking about the new SPICE toolkit, which all of us use, the old one a lot, and I'm sure we're very excited about the new one. So thank you for being here and giving this talk. When you're ready, go ahead.
Yes, so thanks for having me this afternoon. So yeah, as Chase just mentioned, I'm gonna present you what's new in the N0067 SPICE toolkit on behalf of the NAIF team from the Jet Propulsion Laboratory. So today we're gonna go through, obviously, the new capabilities of the N0067 toolkit, but I'm also going to briefly give an update on our tools with Geocalc and Cosmographia, also on the status of SPICE 2.0, and then we're gonna wrap up. So N0067 was released last 3rd of January. The previous release, N0066, was released a long time ago in April 2017. As usual, the toolkit is available in 5 programming languages. That's Fortran, C, IDL, MATLAB, and also an alpha test Java native interface. We still call it alpha, although it's mostly comparable to the other toolkits. The only thing that is lacking behind is documentation, so we still tag it as alpha test. There's 33 environment-specific packages. We call an environment a combination of a CPU, an operating system, and the compiler bitness. There's packages for Linux, OS X, Windows, Cygwin, and Solaris. For Fortran and C, it's available both in 32 and 64 bits. The 32 version is not true for OS X and for Cygwin. For IDL, MATLAB, and GNI, it's available in 64-bit only. There's a new native support in C for the Silicon M1 Microchip Max. We have discontinued support on Sun and all 32-bit IDL, MATLAB, and GNI platforms. And the packages are provided in the usual fixed location on the NAIF server with the link provided here yonder. So basically, no disruption to processes, automatically fetching toolkits should be expected. So for those of you who use SpicyPy fetches the CSpice from the server. And although it's the new version, there should be no problem with it. Other continuous integration pipelines, such as Jenkins, that fetch the toolkit should not be disrupted either, and so on and so forth. Of course, we have also released the N0067-based utilities and their documentation. Those utilities are provided in their standard locations on the NAIF server as well. So concerning new capabilities, there's a number of new high-level routines available in all languages. First and foremost, point. This is the point on the ray nearest to the target's surface. And also, it also computes the point on the target surface nearest to the tangent point. You can see a sketch on the right-hand side of the slide. This is very useful, for example, for occultation observations for instruments such as ExoMars 2016, DGO's NOMAD, or IUBS in Maven. Also, for example, occultation observations by Diviner in LRO, and so on and so forth. And although this was a quantity that before you could compute using other APIs available, the nice thing is that all the aberration corrections are implemented in this kind of complicated scenario. So that's the strong point about this new API. Another new API is the target separation, and it allows users to compute the angular separation between 2 spherical or point objects. So that's basically either a combination of 2 point objects, or a spherical and a point object, or 2 spherical objects. And the nice thing is that it takes into account the limb of this extended spherical target. So you can see a sketch on the right hand down in the slide of the geometry context of this API. So another new API, it's ACL CPO. This allows to compute the azimuth elevation state of a target. So it returns the azimuth elevation coordinates specified in any which way of a specified target relative to an observer, where the observer has a constant position in a specified reference frame. The nice thing is that the observer position is provided by the calling program rather than by an SPK file. This is useful as well because it also computes the derivatives, and it's useful for situations in which you have observers on the surface, such as landers, ground stations, and so on and so forth. There was an equivalent API for rectangular coordinates in older versions of the toolkit. Next, there's a number of new APIs that provide azimuth and elevation to rectangular coordinate conversions, which are listed below. And there's also Space Command to Line element evaluator based on Balado 2006. It's called EVS GP4. This functionality was already available before in the toolkit, but this API provides a high-level interface to this capability. Finally, there's a new addition, which is convenient. It complements the already existing getFob API and retrieves the field of view parameters for an instrument, but specifying its name instead of its numeric ID, which is it's quite well, it's helpful. So moving forward with new capabilities, there's new reference frame types. Of course, this could be more oriented towards SPICE data producers rather than pure users, but anyone can also write one of these frames. So the first type is switch frames. So switch frames choose at runtime other frames with which to align their orientation. So switch frames switch the frames they align with as a function of time using a prioritized list of frames and an optional associated time bounds. So this is very useful, for example, when you have a frame that represents the orientation of a spacecraft that could have a top priority CK frame for measured or reconstructed data and a lower priority CK frame for predicted data. In the past, there were workarounds to address this. This would require 2 spacecraft clocks and some cumbersome definitions in the frames kernel. This is the case, for example, for ExoMars 2016 TGO, which implemented this workaround. And now this provides a much cleaner solution in which you simply have 2 spacecraft clocks and a CK associated with which, and the user doesn't have to worry about this. Another example of switch frame would be exactly the same thing, but instead of having a lower priority CK-based frame for predicted data, you could have a lower priority dynamic frame for times which are not covered by the CK data. And this dynamic frame could describe a canonical attitude profile of the spacecraft, such as nadir pointing or whatsoever. Another example is a frame representing predicted orientation of a spacecraft that would have a sequence of base frames of one or more classes covering time intervals which overlap only at their endpoints. This is very useful, for example, to generate an attitude profile or a pointing profile, which before could be, or which can be generated by the NAIF utility predict. So you can construct an orientation timeline, and you don't have to do it with a CK, but now you can do it with a series of reference frame definitions. Finally, another example is a frame representing the orientation of a comet's nucleus that could have a top priority CK frame covering a time interval over which accurate orientation data is available, and the lower priority PCK frame for a time interval of a greater where the detailed or the resolved orientation of the comet nucleus is not known. This is, for example, the case for the Churyumov-Gerasimenko, the target of the Rosetta mission, for which, of course, there's a very detailed orientation information during the mission timeline, as opposed to the rest of the data for the comet. The other type of new reference frame available are product frames. These belong to the dynamic frames family, and they provide an orientation relative to a specified base frame, which is defined by a product of one or more frame transformations, where each factor may be any transformation computable by SPICE. This might sound a little bit abstract, but this type of frame was actually implemented to accommodate a new strategy from the PDS ring node to implement some frames of their interest. Moving forward, we have extended the TextPCK subsystem to support extended phase angle polynomials. In fact, this was required to be able to release the PCK, the generic PCK version 11 from the IA report from 2015. We have also performed an overhaul of the spacecraft clock subsystem, increasing the efficiency in interleaf conversions for multiple clocks. This is very useful, for example, in situations in which you have multiple clocks, such as landers that have local mean solar time implemented with a spacecraft clock, or for missions such as NICER that have 4 different clocks. We have also provided extensions to the time subsystem, for example, supporting the trailing Z in UTC times on input. This was an item that was requested a long time ago and many times by PDS, for example, and it's very handy for users. We've also included support for numeric GPS time in uniform time system conversions, specifically with the unit time API. And we have also increased the buffer capacity, so there's more coefficient records in spacecraft clock, bodies in SPKs, and structures in CKs. This was necessary to accommodate modern missions or modern scenarios. So, for example, there's a new strategy of correlations for spacecraft clocks, which will generate new coefficients every minute, say, as opposed to what was usually in the past, that you would have a new coefficient every week or every month. This also is useful to accommodate, for example, scenarios in which you would have hundreds of bodies in the SPK subsystem for satellite constellations such as the Starlink constellation of SpaceX, or if you were to model debris as well. And last but not least, we also have many new built-in name to ID mappings and body fixed PCK frames. Most of them support new missions and also Hayabusa 2, OSIRIS-REx, DART, Hera, and New Horizons targets. So we have implemented the body fixed PCK frames in the toolkit for those small bodies. We have also many new wrapper APIs. So that's 49 new in C and CSPI, 62 in IDL, 95 in MATLAB, and 8 new classes and 66 new base methods in GNI SPICE. So this means, for example, that for SpicyPy, in order for it to be up to date to N67, it will have to include 49 new wrappers to CSPICE APIs. And basically, these new wrappers bring the supported functionality of IDL, MATLAB, and GNI toolkits largely in line with that of the CSPICE. Also, another point which is very important for us, and we consider also very important for users, is major header documentation updates across all languages. So we have new working examples in API headers. So that means that in all IDL and MATLAB routines, in hundreds of Fortran and C routines, now there's one or more complete, relevant, and compilable working examples that use PDS examples is available at the link here under. And the IDL and MATLAB headers have been extended to be fully consistent with Fortran and C. So in the past, some of these headers might have missing sections or incomplete information with respect to their CSpice equivalent documents. So you don't need to cross-reference anymore those documents, and you can make use of the IDL and MATLAB headers solely. So basically, this adds a lot of additional help to users that are willing to read these headers. Of course, there's been a handful of bug fixes. Most of them are minor, so they are not worth mentioning. And you can find all these new capabilities more in detail in the link provided here under with in the what's new in N67 document. So it's time to upgrade because the N67 are 100% backward compatible. So any SpiceAware application relinked to the appropriate N67 Toolkit library will work as before. Of course, there could always be a compiler compatibility issue that would require you to rebuild the toolkit. But basically, we encourage you to switch to N67 in order to make use of the new capabilities, to enjoy better documentation and bug fixes, and of course, to be able to use the new frame types when such frames are available, or if you want to write such frames. So please spread the word about the new toolkit in your community. So this could be the end of my talk, but as I mentioned before, I also wanted to update you on our other tools, WebGeoCalc and Cosmographia. For those of you who don't know, WebGeoCalc is an interface to a SPICE geometry engine running on a remote server. It's available both as a graphical user interface and as an API. And the current version, 2.2.9, was released last month. It upgrades WebGeoCalc to N67. So one of the niceties is that it accepts Z at the end of the UTC time string, as I mentioned before. And we're planning to release later in 2022 new versions that will include the new Geometry Finder illumination angles calculation, which is equivalent to the API that implements this calculation, a new pointing direction calculation, and the new API as well equivalent tangent point. There's different installations of WebGeoCalc. So we have two at NAIF, which allow you to load all the archived data sets and bundles that we have, and including also, you can also access the server using a manual update of kernels. There's an instance at ISA maintained by the ISA SPICE service. It also includes a GUI and an API, and it's also up to date. And you can load all the archived and operational SPICE kernel datasets from ISA. There's an installation at Darts from JAXA, although it's currently down. It's going to be updated and up again in the coming weeks. And for your information, there's also an internal installation at the Paris Observatory. So moving forward to Cosmographia. Cosmographia is a SPICE-enhanced 3D space mission visualization tool. The current version is 4.0, released in February 2019, and version 4.1 will be released in the coming weeks. It will upgrade Cosmographia to N67. It will allow users to load shape data directly from digital shape kernels, and it will have other improvements such as means to change the text size and also various GUI interaction improvements. It also will include additional Python scripting functions, but as it is right now, those scripting functions will not yet be available in Windows systems. Cosmographia is available from our site, and there's also an online user's guide that in fact, has already been updated with the version 4.1 features. Finally, a word on SPICE 2.0. So don't want to create any hype, but we're going to work on the C++ implementation of the SPICE toolkit. It has an object-oriented design, support for concurrency. There's going to be performance improvements, and it will support all the existing SPICE kernel types. Yet still, this is expected to be a multi-year development with the first public release several years away from now. And of course, we will continue to support all the existing SPICE toolkits. Final note, as usual, we are continuing to work hard to advance the SPICE capabilities, data, and services to support you, our dear users of the space science community, and we welcome your suggestions.